Let's look in more detail at the ADuM4135 isolated gate driver and a couple of the system benefits that this part can bring to the motor control drive developer. The ADuM4135 from Analog Devices has some key specifications related to Igbt protection and to the timing performance of the driver itself. We will consider both of these specifications and their system impact. In terms of Igbt protection, the ADuM4135 implements desaturation detection with soft turn-off. Also, in order to prevent DVDT-induced turn-on of the low-side Igbt during the turn-off transient of the high-side Igbt, it includes a Miller clamp circuit, as well as bipolar drive capability. Additional reliability in the presence of fast switching transients is provided by the 100 kV per microsecond common mode transient immunity spec. In this clip, we turn on a switch that connects a motor phase to the DC bus negative rail, emulating a DC bus short circuit. The desaturation protection on the high side Igbt triggers when it turns on, rapidly removing the short circuit. The fault indication on the gate driver IC signals the presence of a fault to the processor, which immediately shuts off PWM to all the Igbt gate drivers and enters a fault mode until the user resets the fault condition. Fast overcurrent detection and protection is also typically used in motor drives to protect against faults that may not trigger desaturation, but that may still be potentially destructive to the IGBTs. This is becoming more important as IGBT short circuit withstand times are reducing down to levels around 1 microsecond due to high Igbt transconductance as well as smaller die sizes. Along with the reaction time of the current sense circuitry or digital fast filters, the very short propagation delay of the ADuM4135 is critical to achieving viable fast overcurrent protection. In this slide, the delay between the hardware trip signal, the PWM output signal, and the actual gate emitter waveform of the upper Igbt in one of the inverter legs is shown. The total delay to commencement of Igbt turnoff is seen to be about 100 nanoseconds from detection of the overload, showing the value in having such a short and low jitter propagation delay. The propagation delay skew or jitter is also important in that it helps to minimize the blanking or dead time that must be inserted in the pulse width modulation waveforms as illustrated between the high side and low side transistors. The length of the dead time is mainly determined by two factors: the mismatch between the turn on and turn off delay times of the IGBTs themselves, and the total gate driver propagation delay mismatch or skew. The effect of the dead time is to distort the average voltage applied to the motor, especially at low speed. The dead time in effect injects an approximately constant magnitude error voltage that changes sign when the current in a phase leg changes direction, and so step changes occur in the motor line-to-line voltages at the points where line currents cross zero. This creates harmonics of the sinusoidal fundamental voltage, which in turn generate harmonic currents and torques in the motor. This is a particular problem for larger low-impedance motors used in open-loop drives, where the harmonic currents can be significant, resulting in low-speed vibration, torque ripple, and harmonic heating. Low-speed operation is important because it is in this mode that the applied motor voltages are very low, and the error voltage from dead time can be a significant fraction of the applied motor voltage. Moreover, at low speed, any induced torque ripple has a more detrimental impact, since the filtering effect of system inertia at higher speeds is not available. Typical harmonic torque numbers for two example induction machines running in open-loop mode are shown. Clearly, the ability to have shorter dead times can provide a benefit in this case, as it brings the harmonic torque levels well below 1% of nominal. The dead times shown in this example are illustrative of what is achievable with the ADuM4135 based on the IGBTs used in the inverter platform, and also using a competing optocoupler-based gate driver. We can see this effect to some extent in the inverter platform. Here we show the reduced motor current and phase voltage distortion when the dead time is reduced from the values required by optocoupler type gate drivers to the 500 nanoseconds achievable using the ADuM4135 in conjunction with the 1200 volt IGBTs on the isolated inverter platform. This can be also seen in the harmonic content, especially from the 5th and 7th harmonics, as indicated here. In the case of higher performance motor drives and servos, which implement closed-loop current control, this is less of an issue. The current harmonics introduced by the additional dead time are usually well within the bandwidth of the current controller, which should then provide positive disturbance rejection. This is illustrated here via simulation results from a closed-loop controller for a Kollmorgen permanent magnet servo motor. The torque ripple in percent of nominal torque is shown for the two dead time levels. There is still an improvement with the shorter dead time, which may be important in some very high performance drives. However, the absolute levels are less than 0.1% of the nominal torque, which may not be that critical in some applications. In conclusion, it should be added that as switching frequencies in motor drives and other applications of three-phase inverters increase, the gate driver timing specifications will become more and more important.